Hey everyone, so now we're going to go over a couple of examples actually working out a few confidence interval problems. So again, it's very important to remember the base formulas for these confidence intervals because based on what type of information you have is going to affect the way that you need to go through the problem. So to start with, obviously we have our base formulas here where we have the mean, and remember it's going to be the point estimate plus or minus that z statistic times the standard error. So for the mean based problem, we have the x bar as our point estimate. The test statistic in these cases is always going to be z, and that z is going to be based on our 90, 95, or 99% confidence levels, whatever confidence level we're wondering about for that particular problem. So we'll just plug and play that. And then our standard error for a mean problem is going to be s divided by square root of n, which is the sample standard deviation divided by the square root of the number in the sample. Whereas you can see for the proportion-based problem, we're actually using that sample proportion times 1 minus the sample proportion, all that divided by n, square root of all of that. So it's just a totally different formula. So we're going to go through a couple of problems now. I'll have the actual problems in the description of the video, and so we'll go through those right now. Okay everyone, so for the first problem we're looking at here, it says that we have a simple random sample of 30 has been collected from a population. In that sample, the mean has been calculated as 240, and we have to construct and interpret the 90 and 95% confidence intervals for that population mean, and they also tell us that the standard deviation is 10. So anytime that you're beginning to solve these confidence interval problems, there's two really important things to identify. First, whether or not we're dealing with a mean problem or a proportion problem. So obviously, if in the problem they're giving you an average value, a mean value, is going to be a mean-based problem. Now this was a more simple one where they actually tell you this equals this, the mean equals this, the standard deviation equals this. Oftentimes in problems they're going to be much more conceptual in nature. They're going to describe a situation where you kind of have to derive whether or not it's a mean or a proportion-based problem. But the rule of thumb, if they say average value, we're interested in a mean number, it's a mean-based problem. If they're saying some percentages and we're interested in a part out of a whole, that's going to be a proportion-based problem. So that's the first main thing to consider, is whether or not it's a mean or a proportion. The second thing to consider is your 3-number summary that you set up. Now this is just pretty much identifying the variables that you need to have filled out so that you can appropriately plug into the various formulas you need. And in this case, it's going to be n is the first number that's pretty much always going to be there. That's your number in your sample. Your x bar, or it's your f, depending on whether or not you're dealing with a mean or a proportion-based problem. So in this case, we have, it says, a sample mean has been calculated to be 240. They're telling you that it's the sample mean. Clearly, it's going to be a mean-based problem. We have x bar as the number here instead of f. And then we have our sample standard deviation. Now, it's important to note that the sample standard deviation is not going to be a consideration whenever we're dealing with a proportion-based problem, because look at this. For a mean-based problem, we need x bar, which is going to be in our 3-number summary. We need n, which is in the 3-number summary, and we need s, which is in the 3-number summary. But for a proportion-based problem, we have f, we have n, but notice that there's no standard deviation involved. That's because when you fill out a confidence interval formula, you solve for the standard error right here, and the nature of the standard error when you're dealing with a mean-based problem versus a proportion-based problem is simply different. It doesn't involve the standard deviation here. So if you have a proportion and you're thinking about, oh, where's my standard deviation? I need to plug into that formula. You're probably thinking of the wrong formula because it's this standard deviation, or I'm sorry, this standard error, not this standard error. So to go through this problem, we're going to simply fill out our 3-number summary. So we have n equals, they say, is 30. It was a sample of 30 that was collected. We have x bar. They tell us that the sample mean is going to be 240. Okay. And it says that our standard deviation is going to be 10. All right. Now, let's go ahead and save ourselves a step ahead of time, because see right here, the only place we use this 10 in this formula to fill out this confidence interval is in the numerator right here. But what we're actually looking for is s divided by the square root of n. So why don't we go ahead and solve for that and just forget about that s afterwards, because the only reason we use it is so we can find our standard error. So we're just going to go ahead and turn that into 10 divided by the square root of 30. And we're going to solve for that. And that number is actually going to be 1.826. So 1.826. Okay, so we can pretty much scrap that 10 now, because all we're interested in was this number right here. This was a means to an end in this case. So now that we start going through the actual problem itself, they ask for a 90% confidence interval and a 95% confidence interval. So let's start with the 90% just to make things simple. So we're going to do our 90% confidence interval, and we're literally just plugging in these values we identified into this formula. So we start off and we have, okay, x bar is the beginning part. So let's just fill out the actual base formula again. X bar plus and minus z times your s divided by square root of n. Okay, so your x bar in this case we just filled out was 240. So that's one of the great uses of your three-number summary is that you already have everything listed out, so you don't have to keep going back to the problem over and over to find that. And remember, it's going to be plus and minus because a confidence interval creates a range of values, a lower bound and an upper bound. And so you're going to conduct this formula, do the minus sign to get your lower confidence level, do the plus side to get the upper confidence level, and you'll see how that works out in just a second. So we have 240 plus and minus our z. Now our z right here, that's based on what confidence level we're interested in. In this situation, we're interested in a 90% confidence level. Well, the way you plug in z is just based off of what we went through in our previous video, the confidence intervals overview, where we just have these rules of thumb you can hold on to, where we have a 90% confidence level is 1.64, which is what we're going to look for, but simply based on your confidence level, that will dictate your associated z value. So in this case, 90% is going to detail a 1.64 z value. So we'll say 1.64 times, and we just found what s divided by square root of n is, right? We said that that was 1.826 right here. So we'll say that's 1.826. So one thing I like to do when I'm solving these is go ahead and take care of the part on the right side that you're going to have to do for each iteration of the equation. And by that I mean, if I can go ahead and find out what 1.64 times 1.826, what that is, I can just take that full number, subtract it from 240, that's my lower bound, add it to 240, that's my upper bound. So we're going to go ahead and do that, and when we multiply 1.64 times 1.826, we're going to get about, and there are approximations, and again, in the previous video, we talked about how these numbers are very rounded values. So depending on how specific your professor wants you to get about maybe having to solve for these values in Excel and using the full range of decimals involved, your answer is going to differ just a little bit, but in general, it should be about this number right here, 3.0129. And so we're just going to take 3.0129, subtract it from 240. That's going to give us our lower bound. And when we do that, that ends up being 236.99. And we're going to do the exact same thing, take our 3.0129, but actually add it to 240 because we're doing the add part now. And when we do that, we're going to get 243.01. So what this range is saying is that we are saying with 90% confidence that the mean of the population is contained within this range right here. Okay, so somewhere between about 237 and 243 is going to be the mean that we would expect to see in the population itself. So that's how you do the mean-based problem for a 90% confidence interval. So if we were to do a 95% confidence interval, it's going to be the exact same procedure. The only difference is going to be that instead of putting in the 1.64 right here for your z value, you're actually going to put in 1.96 because we're doing it with a 95% confidence level. So really, the x bar, that's given by your problem. Your z, that's dictated by your associated confidence level. And your standard error right here is just going to be s divided by square root of n if you're dealing with a mean-based problem. And it's going to be this big formula right here if you're dealing with a proportion-based problem, which we'll get into right now. All right, so now we're going to go ahead and solve for a proportion-based problem. So in this case, we actually have a situation where it's not just telling you x bar equals this, n equals this. It's a bit more, it's an overview. They're explaining a situation where you have to derive the values from it. So it'll be a little bit more useful, maybe a little bit more representative of what you might expect to see on exams and homework and things like that. So the problem that we have here, it says that we have a study by careerbuilder.com found that 20% of companies check out job candidates' profiles on social networking sites like Facebook and MySpace. This is an old problem, clearly, before deciding whether or not to employ them. So assuming that the survey included a simple random sample of 1,200 companies, construct a 90% confidence interval for the population proportion of companies that check social networking sites before offering employment. Okay, so when we see that, again, one of the main things we need to consider is this a mean-based problem or a proportion-based problem? Well, they're specifically talking about the percentage of companies who check on people's social media before deciding to employ them. They're giving you percentage numbers. They even say the word proportion. All telltale signs that we're dealing with a proportion-based problem instead. So you should be screaming this formula right here, not the mean-based formula we just did. So we're going to see how that differs right here. So when we're doing our three-number summary, like I said before, we're going to say that n, again, that is the number in the sample, right? And it says that here we did a simple random sample of 1,200 companies. So that's the number in the sample is going to be 1,200 right there. The next number is going to be either x bar, which is not going to be the case here because this is a proportion-based problem, right? X bar is the sample mean. We're not going to deal with that. And so we're talking about f here. So when you're dealing with f, we have, normally you're looking for some number, some attribute that you're interested in out of the sample, out of the entire sample. And so if we're interested in the companies that do check check social media before they hire you, the attribute that we're interested in would be companies who check social media, right? Divided by N, okay? But in this situation, the problem directly tells us that 20% of companies check out job candidates' profiles on social networking sites. So in reality, if they had told us the number of companies who check the social networking sites, we could have plugged that number in right here out of the entire number in the sample, which is 1,200. And that's the proportion of the attribute in the sample that we are interested in. In this case, they just go ahead and give us the 20%, which is nice, but they might not always do that. So just keep in mind, if you're ever having to find that on your own and they don't just simply tell you that it's 20%, or in this case 0.2, then you're actually probably going to have to solve for that on your own. So just keep that in mind. So from that point, we're just going to continue down our number summary. Remember what I said about S right here. That's only going to apply to a mean-based problem, right? Because there's no S anywhere in this formula. So let's not worry about it. At this point, we have our N, which we need for the denominator right here. We have our F, which we need in several locations throughout the formula here. And the Z is just going to be based on our confidence level again. And so if you go back to the problem, it says we're trying to conduct a 90% confidence interval. So we're saying it's 90%. And what we're going to do with that 90% is, let's again just fill out our base formula. We have F plus and minus Z times square root, big square root, of F times 1 minus F divided by N, okay? So we're just going to continue to fill that out. So we have our F right there. That's going to be 0.2. We're going to do the plus and minus side, just like how we did with the mean-based problem. Our Z with a 90% confidence interval, 1.64. And again, just be very particular as to what your professor, how specific they want you to be with this number right here. You might get a slightly different answer based on the preciseness of your Z critical value, because this is a very rounded number right here. But just keep that in mind. Overall, this should be about correct. So 1.64 times, and it's just a big square root right here, it's going to be 0.2 times 1 minus 0.2. So we just go ahead and say that's 0.8, which is 1 minus 0.2. All of that divided by N, which was our 1,200 right here. So just like with the mean-based problem, I recommend that you kind of segment out your order of operations. Like, this is a really funky number you're going to have to calculate right here. The way I would go about it is to multiply 0.2 by 0.8, get that number, then divide that number by 1,200. That overall number is then going to be square rooted. So just pay very particular attention to making sure you're doing it step by step, because even if you understand the whole formula as a whole, just a minor miskey in that situation is going to make the whole problem wrong. So just be very careful about that. And so at this point, we're just going to continue to solve our confidence interval. So we have our 0.2 plus and minus our 1.64 times, and when you calculate all this in the manner I just said, this right here ends up being about 0.0115. Okay, so you're going to take your 0.0115, multiply it by your 1.64, and when you do that, your overall, when you start to solve the confidence interval, is going to be 0.2 plus and minus 1.64, or I'm sorry, I'm going to solve for that now. When you multiply those two together, you end up getting 0.0189. Okay, so at this point, we're just going to subtract 0.0189 from 0.2 to get our lower limit, add 0.0189 to 0.2 to get our upper limit, and that's going to be your confidence interval. And so when you do that, our overall confidence interval, when we do the minus side, is going to be 0.1811, and that's when we subtract it. And when we add it to 0.2, we're going to get 0.2189. Okay? So at this point, it's really just a matter of having all of your variables listed out so that you can appropriately plug them into the formula. And by the time you get into more detailed confidence interval problems where you start to have more than one sample, so there's some situations where, in this case, we just had one sample that we were taking out of a population. We were running data on it. But in a lot of situations, you can actually compare two different samples. And this base formula is going to be expanded a little bit to take into account that there's two X bars and there's two N's in various situations like that. But we'll get to that in a separate video, but for right now, if you watch the overview video of confidence intervals to kind of get an idea of the base formula, why we're interested in a confidence interval, how that's useful, and then you're just able to plug it in based on the steps we went through, you should be good to go. You're going to nail all those problems, and so I hope that helped.